Welcome to this explainer. Today, we're going to quietly dive into a profoundly elegant piece of engineering. We're looking at a project that sits right at the intersection of metamaterials, quantum chemistry, and the boundless quiet of deep space. It's called the MEI RIT project, that's short for Metasurface Enhanced Iodine Radio Frequency Ion Thruster. It is, quite literally, a masterpiece of miniaturization. So let's explore exactly how humanity is rewriting the laws of space mobility.
Out in the vast, silent ocean of Earth's orbit, a revolution is taking place. We're living in this booming era of the small satellite. Think about it. CubeSats and microsatellites that can literally fit in the palm of your hand, yet they possess the power to connect our entire world. But to keep these delicate instruments in orbit, or to send them out into deep space, we absolutely need propulsion. Traditional chemical rockets and cold gas thrusters, they're simply too bulky and way too inefficient for this scale. We need a system that completely transcends those old limitations. We need, essentially, an electric breath in the vacuum of space.
Here's the journey we're taking today. We'll start with the Deep Space Challenge, move into iodine as the solution, and explore the absolute limit of miniaturization. Then, we'll dive into the metasurface innovation, break down the architecture and mathematical optimization, and finally, look at the future of MEI-RIT.
Section 1. The Deep Space Challenge.
Electric propulsion is highly prized in this industry for its incredible fuel efficiency, which we measure as specific impulse. But here's the catch. As we try to shrink these thrusters down to fit modern tiny CubeSats, the traditional radio frequency plasma scaling laws push back hard. Physics simply resists being squeezed into a smaller box. But when you compare the projected MEI version 1.2 against proven giants in the field, like the ThrustMe NPT-30i2 or the Busek BIC3, the data is pretty stunning. The MEI drastically cuts the system dry mass to under 220 grams. That is a mere fraction of the others. And yet, it nearly doubles the total efficiency, projecting a steady 36 to 46% output. It is genuinely doing so much more with so much less.
Section 2. Iodine as the solution.
To actually achieve this kind of efficiency, we have to move away from the expensive noble gas traditionally used in space, xenon. The solution lies in a humble yet incredibly strategic element: solid iodine. Just consider the physical advantages here. Unlike xenon, which requires heavy, highly pressurized tanks, iodine sits perfectly peaceful in a solid state at room temperature. Its density is 3 times that of pressurized xenon, meaning we can pack immense potential energy into a tiny space. Plus, it's roughly 100 times cheaper. Furthermore, iodine has a higher probability of being ionized at standard electron energies between 10 and 200 electron volts. And because it sublimates, meaning it turns directly from a solid into a gas, it enables this brilliantly simple, pipeless delivery system. There are no complex valves, just pure, beautifully controlled sublimation.
Section 3. The limit of miniaturization.
But just using iodine is only half the puzzle. We now hit the primary physics roadblock holding back small satellite mobility, and that is the strict, unyielding laws of radio frequency plasma discharges. Specifically, a concept known as the cutoff frequency. Think of a discharge chamber as a tunnel for electromagnetic waves. There is an absolute minimum frequency required for those waves to actually pass through. If you shrink that tunnel too much to try and fit it onto a tiny satellite, the waves simply cannot propagate. The surface-to-volume ratio gets too high, and the energy just crashes uselessly against the chamber walls. The plasma refuses to ignite efficiently. This is the classical wall we always hit when miniaturizing.
Section 4. Metasurface innovation.
So how do we get around that? Well, imagine a piece of hardware barely the size of a coin, producing a glowing, intensely violet beam of iodine plasma. The secret to overriding that classical limitation we just talked about is integrating a sub-wavelength metasurface directly inside the discharge chamber itself. This engineered, highly specific periodic pattern of metals and dielectrics literally manipulates electromagnetic waves. It bends the rules of the tunnel. It drastically intensifies the local electric fields, concentrating the energy so precisely that it effortlessly ignites the iodine plasma, even in such an impossibly tiny space.
Let's look really closely at the physics breakthrough here. By meticulously tailoring the surface impedance of the chamber walls with this metasurface cladding, we reduce the cutoff frequency by a massive 3 GHz. We're dropping it from 5.7 down to just 2.2 GHz for the TM01 mode. Because of this, standard radio frequencies can now absolutely thrive inside microscopic chambers. We've successfully bypassed the classical limits of physics.
Section 5. Architecture and mathematical optimization. A physical thruster, though, is really only as good as the mathematics that breathe life into it. To design this, the project relies on a living piece of code, the Metasurface RF Coupling Optimizer, or MRCO. This Python algorithm uses a differential evolution method to meticulously search for the absolute perfect physical geometry. It tests thousands of microscopic variations in the metasurface structure, quietly hunting for the exact proportions that will yield maximum plasma coupling.
And at the very heart of that algorithm lies a foundational law, the optimization equation. Efficiency equals 0.42 plus 0.23 times resonance times matching times the thickness factor minus the loss. This specific mathematical sentence dictates the ultimate harmony of the thrusters. It beautifully balances the resonance of the waves with the strict physical constraints of the materials.
So what did that code discover? Here are the exact winning parameters found for MRCO version 1.11. A metasurface period of exactly 12.44 micrometers, a fill factor of 0.50, and a thickness of 2.75 micrometers. We are talking about unimaginably small dimensions here, literally fractions of a hair's breadth. Yet these microscopic dimensions result in a macroscopic 10 to 15% improvement in coupling efficiency. The micro directly dictates the macro.
But the analysis actually goes even deeper than that. Because iodine is a highly reactive halogen, classical physics gracefully gives way to quantum chemistry. To handle this, the MEI RIT project utilizes variational quantum eigensolver, or VQE, algorithms to calculate the exact atomic bonds and potential energy surfaces of the iodine under electromagnetic excitation. We are essentially mapping the very soul of the propellant at a quantum level, just to ensure the thruster's materials can withstand its reactive nature out in deep space.
Section 6. The future of MEI RIT.
The vision laid out by the project's creator, Lázaro López Paz, isn't just some abstract dream. It's a highly realistic, fully budgeted 18-month roadmap. It starts with the initial design and simulation in Phase 1 before moving directly into cleanroom fabrication at world-class facilities, like those in Barcelona, during Phase 2. Then comes the careful assembly and vacuum testing in Phase 3, culminating in final optimization and patents in Phase 4. It is physically and economically ready to be built in European cleanrooms today. And honestly, the total estimated cost is wonderfully modest for such a massive leap in space capabilities.
Ultimately, the MERIT is fundamentally tied to a vision of sustainable space exploration. It's a way for us to maneuver safely and eventually clear our orbital pathways of dangerous debris. So, I want to leave you with this. As we deploy sustainable, high-efficiency propulsion out there in the dark, how will our growing mastery of these invisible quantum and electromagnetic forces shape our interconnected future in the cosmos? Thank you so much for exploring this quiet revolution with me today.